Okay. Now let's see subthreshold region. So for this region, condition is VGS less than VTH. This is also known as weak inversion region. Weak inversion region. Now, saturation region is known as strong inversion region, also known as strong inversion region. Now, so equation for this region is basically ID equals to I naught exponential VGS by VT. Here I naught directly proportional to W by L of MOSFET, and this is constant, and VT is thermal voltage. VT equals to KT by Q, which is at room temperature 26 millivolt. Now, so this is three regions of operation and its equation. Okay, now let's discuss output resistance. For linear and saturation region. Okay, so for saturation region, output resistance is defined as RO del ID by del VDS, and it is given by 1 by lambda ID. So it means if ID we are going to increase, then RO is going to reduce. Now lambda is inversely proportional to length, so RO directly proportional to length. So as L increases, RO increases. Okay, so if we see this graph ID versus VDS, so it means as we are increasing length, then RO also increases and lambda reduces. So if we want to use it as a constant current source, or if we want to use this in a current mirror, we should have large length so that RO is high. RO high means more constant current. Okay, now let's see output resistance of MOSFET in linear region. Output resistance in linear region. Okay, so in linear region, or we can say in deep triode region, when VDS is very small, less than VGS minus VTH, so this is known to be R on, because in linear region, if we see this plot, so this is basically linear region, and this region is saturation region. Okay, so this R1 equals to del ID upon again del VDS. Now ID equation we have seen mu n COX W by L VGS minus VT VDS. This is in deep triode region, and so R on, after differentiating, we will get 1 divided by mu n COX W by L VGS minus VT. So this is R on. So basically if we see, so here this is for VGS1, VGS2, VGS3. So here slope is high, here slope is low, because so here VGS3 greater than VGS1. So R on 3 greater less than R on 1. Okay, now let's see transconductance of MOSFET. Okay, so in saturation region, so basically this parameter mostly defined for saturation region. In saturation region, transconductance defined by Gm del ID upon del VGS, which is given as, so it is having three different equations. So first equation is nu m cox W by L VGS minus VTH. So in this case, plot will be something like this. So this is Gm and this is basically VGS minus VTH, W by L constant. Now second equation is 2 nu n cox W by L ID. So we can draw plot something like this. So this is Gm, this is ID and W by L constant. Okay, third equation is 2ID VGS minus VTH. So it's is given by something like this. So this is VGS minus VTH ID constant. This is Gm. Now what is significance of this equation? So we can understand by some example. So example is something like that. Suppose you are designing some diff pair and you are taking some ID current. Okay, now with this ID current you can define its some Gm, say some W by L is its width and length. Now suppose if you designed here something like at this point for some ID reference current, so it means you are not taking full advantage. So either you should increase current for this W by L, or you should increase W by L in such so that we will get maximum Gm for bias current. So this is the significance of this curves. Okay, now one more thing. Here you can observe that this Gm, this equation is inversely proportional to R on. So Gm in saturation region equals to 1 by R on. This is linear region. It has relationship of Gm with R on. Now let's see transconductance in subthreshold region. Region Gm. So now ID equals to I naught exponential VGS minus xi VT. Now if we differentiate this, so Gm comes like ID VT.